Now we would like to try to continue the proof of Gauss's law, where we're showing that the electric flux through a closed surface is equal to the charge enclosed. But what we've been working on first is kind of a zero result. If you have a charge Q, and we take any arbitrary closed surface now. We looked at some special closed surfaces before, so I'm just going to draw an arbitrary closed surface. And this is a closed surface. And now what I'd like to do is look at the result that we had before. If I divide this, if I make small wedges through this surface, so I'm going to make very tiny wedges through this surface. And if outside here, the artwork here, a little tricky to draw. Let's say these lines intersect the surface over here. Now, this may not be perpendicular to the E field, to the actual shape of the surface, but I'm approximating the surface by a piece there. And out here, I'm doing a very similar kind of approximation. And if the angle here is extremely small, I'll use that symbol to indicate this solid angle is very small, then what I can do is we know that the flux through these two faces are 0. And then I make what we call an infinitesimal deformation, where I just kind of try to approximate the small shape of this surface by a very tiny small surface patch. Now, in the limit in which we make the wedge very small, I can divide up this arbitrary closed surface into these two pieces with area A1 and area A2. And now we can go back to the proof that we showed before. Because Q is not enclosed, and if I have to tilt this area to match the local shape of the surface, well, that's OK, because of the way the cosine factors canceled on both of these pieces. And so for this infinitesimal surface, we have that E dot n hat dA1 plus E2 dot n hat 2 dA2 is 0. And that was what we proved in our last video. And now what we do is we just add up a surface integral adds up all these pieces. And so as we extend our surface over the whole piece, we're dividing up our surface into these wedge-like shapes. And so using this infinitesimal argument, the sum over the whole surface of E dot n hat dA over the closed surface. Now, sometimes I'll write little dA, or I might write a big dA. That doesn't matter. That's just a letter indicating the small area element. When I sum up all of these over the whole surface, the pieces that are in pairs will cancel, and this is 0. And the reason it's 0 is that there's no charge enclosed. And so that generalizes what we did for the wedge and tilting the angle of the wedge to an arbitrary closed surface where the charge Q is lying outside the surface. And now we're in position to try to prove the general result.